Hello, everyone. My name is Robert Howell, and I'm an engineer in the professional development at ACI. I'd like to welcome you to today's webinar, Constructability Series, Design and Detailing of Steel Reinforced Concrete Structural Members for Constructability, including slabs and beams. We're glad that you could join us. A PDF of the presentation you're about to see can be found in the handout box. You can use the PDF to follow the presentation and take notes if you'd like. Note that this is a 90-minute presentation. Audience, please note we are presenting this webinar as part of a Constructability series. This webinar is the second of a 6-part webinar series that ACI is presenting within this month and next month regarding constructability in concrete design and construction. It is planned that this Constructability series will be developed into a certificate program, joining others that ACI offers. More information will be forthcoming on our website. For continuing education credit, attendance for the entire duration of today's live webinar will earn your certificate of completion for 1.5 PDF. Your certificate will be available in the ACI University under the Certificates tab within 2 days. For those who cannot join us live, the on-demand recording will be made available about a week after the live presentation. You may ask questions using the question box in the GoToWebinar software. Our speaker will be happy to address questions at the end of the presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for 1.5 learning units. This webinar will provide guidelines on how to size, design, and details steel reinforced cast-in-place concrete, supported slabs, and reinforced concrete beams in building structures that will result in enhanced constructability of the structure. Our learning objectives for this webinar are as shown on the screen and is in your handout. Now I'd like to introduce our speaker. David Finala is the Senior Director of Engineering at the Concrete Reinforcing Steel Institute. He has 30 years of experience in the design of a wide variety of buildings and other structures. David has authored numerous technical publications and is a member of several ACI committees. He also serves on the ASCE 7 committee, the minimum design loads for buildings and other structures. David is a fellow of ACI, also a fellow of American Society of Civil Engineers, ASCE, and the Structural Engineering Institute, SEI. In 2014, he was a recipient of the Alfred E. Lindau Award from the American Concrete Institute for outstanding contributions to reinforced concrete design practice. David is a licensed structural and professional engineer in Illinois, and is a past board member and president of the Structural Engineering Association of Illinois. And now David will begin today's presentation. And let me give you screen control.
Okay, Robert. Well, thank you very much, Robert. I appreciate the introduction, and thanks everyone for joining us today. We hope that we're going to have a lot of useful information coming out of today and tomorrow, as well as the whole series. It's certainly my pleasure to be part of this Constructability series. So what we have on tap today are 3 main areas that we're going to cover. First, we're going to give a very general definition of what constructability is, and then give a little more specific one, specifically for reinforced concrete building structures, and then even more specifically to steel reinforced structures. As Robert had mentioned, there's a number of different things we're going to cover with respect to sizing and detailing in this particular session for slabs and beams, and then we'll cover our other structural members in part 2. So, second thing we'd like to cover are some general recommendations and guidelines that could be used in just about any project. Now, we know everything is in a project is unique, and I think the key word here is general. So general recommendations and guidelines. These are time-tested, and if they are implemented, it has been shown that it could lead to savings in both time and cost. Now, certainly you're going to have details and other things that you've developed over the years And those certainly would be valid. And, you know, what I'm trying to say here is this is not a comprehensive list of things that would be applicable and used, and that would be the be all and end all of everything. So these are just general things, time tested, that you can utilize in these different cases. Robert and I were chatting before the webinar. We said that, you know, the information not only here but in the entire series, we would have been very useful for us when we were practicing, because these things will save you in the long run and cut down on the RFIs as well. Now, in that same vein, we're going to look at some specific things for slabs and beams, and then also get into tolerance compatibility. Tolerances are very important as well, as you well know, and having a general idea of how to circumvent some problems from the onset and implement some of these things into your construction documents, I think would be very useful. Again, when it comes time to construction, we know we have a lot of issues that can arise. Our goal here is to try to mitigate some of those and to reduce the number of questions and RFIs that we get. So those are the main areas we'd like to cover today. And we will start by giving a very general definition of what is constructability. Now, there's quite a number of definitions that are out there. I found this one, and I think this is used by some of our allied associations as well. It was developed by the Construction Industry Institute. They're headquartered at the University of Texas in Austin, started back in the early 1980s. It consists of contractors, owners, academia, design professionals. Their goal is to try to enhance overall construction methods here in the United States. So you could read the definition here. Constructability is the optimal use of construction knowledge and experience in planning, design, procurement, and field operations to achieve overall project objectives. And I think in one sentence that basically says it all. Now, we'd like to get a little more specific for steel reinforced concrete construction. As we know, any reinforced concrete structure consists of the formwork, the reinforcing bars, and the concrete. So given the fact, and we'll talk about this a little bit later, in terms of the overall cost, we know the formwork is generally 50 to 60% of the overall cost of the structure. So what does that mean for constructability? We'd like to be able to easily construct the formwork, okay? Making sure that the least number of pieces are there, because that usually results in overall economy and constructability as well. It also means being able to install the reinforcing bars. Okay, the spacing is important. Making sure that the concrete can get in between the bars and the formwork is important as well. So those three main items need to be addressed in constructability, and they all depend on one another. Although we're focusing here on the detailing and reinforcement part, we definitely know that all of these work together, and by changing one thing, it's going to have an impact on the other. So we're going to talk about all of these three aspects as we're going through our presentation today and tomorrow as well. Now, this was a real project that will remain nameless, but I think if you look back at the definition on the previous slide of what we're considering to be constructability in a steel reinforced concrete structure, this probably does not meet that definition. You can see that it's very congested. There's places that's going to be very difficult to get the concrete into. The bars are sort of helter-skelter everywhere, and you know, we can't blame the placers for that. So this is, you know, if it's going to happen, it usually happens at these beam column joints, and this is where a little implementation of some things prior to construction would have basically eliminated this situation at this particular joint. Now you can see in this slide, this is another heavily reinforced concrete member, but in terms of constructability, it meets that definition because you can see the bars are nice and evenly spaced. There was consideration of congestion. You'll notice here, there's a line of headed reinforcing bars. As you know, headed reinforcing bars can really alleviate the congestion in structures where there's a need for a lot of reinforcing steel. So a lot of thought, a lot of detailing went into this. So this can easily be defined as a constructible situation. So today we're going to look at this, as well as tomorrow. We're going to look at member size and formwork. How does that affect constructability? We're going to look at providing certain size and spacing and reinforcement for the elements, our one-way, two-way slabs we're going to cover today, as well as beams. We're going to look at some reinforcing bar detailing. Again, these are general recommendations and guidelines that we've used through the years that we know that work. And finally, we're going to look at tolerances. Now, above and beyond all this, we want to make sure no matter what we do, we always are satisfying the minimum requirements that are given in ACI 318. Okay, without satisfying these, all of the fancy stuff we do and so-called economical things we do are of no use unless all of these requirements are satisfied. So what we're going to present here today does conform to these minimum requirements. So let's start with our general recommendations. And as we go through this list, it's gonna be really obvious. And I'm sure most of us know this information here, but you'd be surprised about certain things that we've seen through the years, and we'll discuss that as we go along. But I think it's always so important, to cut sections through the structure, especially at locations where a lot of things are converging at the same spot. We can't always rely on typical details to spell everything out for us, and that could lead to a whole world of trouble when it comes time for construction. We certainly understand that, time is of the essence, and the project, everybody wants it done yesterday, but providing these specific details is going to help in the long run spot any constructability issues that can occur in the structure. Another general recommendation is to size the concrete members based on formwork economy, because as we know, that constitutes between 50 and 60% of the cost of the reinforced concrete structure, and also on the placement and development of the reinforcing bars in the section, and not just on the applied loads. When I was practicing, I did a number of peer reviews through the years, and you would be surprised what you would see in some of these particular structures. Not saying that anything was unsafe, but I recall offhand a 3-story building where the size of the columns changed every floor. Okay, that's certainly not the most economical or constructible thing to do. Same with the size also changed on a particular floor based on the tributary area of the column. Another thing you see, I saw one time there was a beam schedule that had over 100 beam sizes on that schedule. And I'm sure that could have been consolidated, developing typical beams that you can use in many different places and keeping the same width and the depth over the entire span and just varying the amount of reinforcement. That's what we're talking about here. Also, if possible, and I know this, especially nowadays, this is not always possible, if the columns can be arranged in a regular pattern and having a consistent column size from bay to bay, this would really enhance a lot of things in the structure. When you have this regular column pattern and regular bay sizes, now all of the reinforcing bars in the slabs and the beams are the same length, they're the same size. It's simple to place these bars in the field, and it just causes a great ripple effect throughout the structure when you can have this regular pattern. Now, even if you can't have a regular pattern based on the architectural requirements, having a consistent column size will help in a very similar fashion. So it's this ripple effect it has through the structure that just leads to savings in time and cost. Using repetitive bar sizes and lengths, and also the largest bar size that you can possibly use without violating any of the ACI spacing requirements, that will enhance things as well. Take for example this joint detail. If you can imagine, if you provided the same amount of area of steel, but doubled the number of bars that are coming into the column from the beam, you can imagine the congestion that would occur at that particular column. So again, these are things that if you implement them, if you can, it's going to automatically have a positive effect on the constructability of your structure. Avoiding the dreaded bar that has a hook at both ends. These are sometimes referred to as confined bars. Because of fabrication and formwork tolerances, these types of bars are very difficult to place in the field. So if you can use something like the suggested alternate detail here, where you take the single double hook bar and make it into 2 bars with a hook at the end and then provide a splice, that will help a lot in terms of overall constructability. And that can be in any structural member that we're talking about here. Now, in lieu of this, what might also be useful is to have one longer straight bar and then 2 bars at the ends that are lap spliced to the longer bar, because then you're dealing with a much shorter length of a hook bar, which is easier to handle and place in the field. Using stock length bars, and also lengths of bars that you can repeat very often. And I always like to show this particular example. What you're looking at here is an elevation of a wall that changes elevation over its length. Now, your first impression might be to provide just single bars along the entire length and then vary the length of those bars. Well, that's difficult in a number of different ways, especially placing the bars in the field, because you have to know each bar has to be labeled with respect to what position it has to be along the length of that wall. So to circumvent that problem, you can do this entire layout with just 3 bar lengths. So over the bottom half of the wall, we could use what we're calling here bottom bars length C. Those are all of the same length. Then you could split the wall, again, depending on how long the wall is, maybe you split it in half or you split it in thirds or quarters. But in any case, you would provide in those segments the same length of bar that gets lap spliced to the bottom bars. Okay, this helps out tremendously. So here you have top bars of length A and top bars of length B. And now the person in the field can place this very easily. There's not going to be any mistakes. They're going to run all of those bottom bars first and then come in and splice the 2 different length bars on top of those. And you may wind up with a little more material, but that material cost is going to be more than offset by the savings and the issues that you're going to have with placing all of those different size bars. So, like I said, I like to show this example, but you can carry this over to a whole number of different types of structural elements in your particular project. I think most people use form savers instead of drilling holes in the formwork. I still see sometimes the bars sticking out of the walls. This is the case where the wall goes up prior to the floor system. So this may lead by about 2 or 3 stories, and then they come back and they put the floor system in at those particular levels. So instead of drilling holes in the formwork and having your hook bars sticking out, these form savers, as the name suggests, saves a lot. And these are embedded in, they're nailed to the formwork, and then your other bars basically get screwed into those dowel bars that are already into the wall. Now, if you do have this, it's nice to avoid any hooks on these bars that screw in, especially if those bars are long, because they're very difficult to handle in the field. So if you could get away with straight bar and then maybe lap splice that straight bar to another hooked bar, that would be advantageous for the person installing this in the field. There's really no reason, unless there's a very special circumstance, that you should specify anything other than the standard ACI bar bends that are given in Chapter 25 of ACI 318. You really get no benefit from it. So if you were to specify something other than that, you can imagine what was going to happen here in the fabrication shop. Things have got to be changed. It's, in short, it's a very expensive proposition for really no benefit. You wouldn't want to use anything less than the minimum, but if you were thinking about using something more than a typical standard bar bend, you really get no benefit from it. So we strongly encourage to use just what those values are given in 318. We're going to talk about splices a little bit later when it comes to beams, but knowing what is the appropriate splice to use in the appropriate situation can really enhance constructability. What we're showing here on the left is a typical slab where there's no issues really of any congestion. The bars are spaced out nice and evenly. There's plenty of room to get the concrete in as well as a vibrator. So we have no issues there, and your typical lap splice length works very well. It's usually in, I could probably never say never, right? But it's more than likely going to be the least expensive type of splice that you're going to use. Now on the right, we have this fairly narrow beam with some fairly large longitudinal bars going through the beam. So in lieu of having a typical lap splice that's going to cause congestion, not only in the beam, but probably down the line where this is hooked into another structural member, they decided to use mechanical couplers. And that's always an option to use, especially when you have congestion in these narrow types of members that will cause you issues with constructability. We'll talk about those a little later, as well as headed bars as well. Now, again, it goes without saying, and most of our software is going to do this for us anyway, in most cases, but we need to draw our details to scale, especially if the beams are narrow, at any beam column joints where there's a lot of things going on, or in cases where we have more than 2% longitudinal reinforcement in the columns. These details, especially to scale, will automatically show us if there's any constructability issues in those structural members. And basically, when we draw these to scale, we should be using the approximate outside diameter of the reinforcing bars, which includes the deformations. So the table that we have here for number 3 through number 18 bar gives us the approximate outside diameter of each of those bars that include the deformations. Now, usually if you compare, the approximate outside diameter to the nominal diameter, there's not that much of a difference, but there can be cases, especially where things are tight, that things may not work if you consider this compared to using the nominal diameter of the bar. So just something to keep in mind when these really particular details need to be looked at. If you have a column with 4 bars at each corner, you don't have to worry about what the diameter is, but for especially these situations, it really is helpful. So this is from the ACI 315 document that shows a drawing of this. Could be either a column or a beam. This is the incorrect bend diameter, and you can, and that bend diameter again comes right from ACI 318, chapter 25. It shows where the longitudinal bar is with respect to that incorrect bend diameter, whereas on the right, this shows the correct bend diameter on the drawing with the longitudinal bar at its correct location, and you can see there's certainly a difference between the two. So, again, especially in cases where you're anticipating congestion, having details like this will help in the long run. I'm sure most of you are aware of the ACI 117 document, Specifications for Tolerances for Concrete Construction and Materials. I can't think of any engineering office that shouldn't have this document. These tolerances need to be considered in basically every situation, any reinforced concrete project that you have. It's stated in numerous places that tolerances are the responsibility of the licensed design professional and not the contractor. Nobody knows the structure better than the licensed design professional, and they're responsible for tolerances. So any details that are developed for a project, they should address tolerances wherever applicable. Also, the licensed design professional should try to mitigate tolerance conflicts prior to construction. And again, that's looking at these special intersections where beams and columns are all coming in and taking into consideration what the tolerances are for the placement of the reinforcing bars, the size of your structural members, looking at that in particular and giving a little breathing room, adding maybe a little cover here and there just for an example. That's mitigating these tolerance conflicts before you get the phone call where the project has stopped because things aren't fitting together. So a little time spent on mitigating some of these things prior to construction can save a whole world of hurt later on. And then when things inevitably do go a little awry in the field, it's up to the licensed design professional to provide a practical solution for that tolerance conflict. Now, generally speaking, and this again is not true in all situations, and sometimes you can't help but do it, but mitigating any tolerance conflicts in the field usually will be handled best by trying to manipulate the formwork in some way before obviously the concrete is poured. Okay, having to move the reinforcing steel, especially if it's in a pre-assembled cage, is going to be time. It's going to, I should say, waste a lot of time and a lot of cost as well to try to make things work. So if you can change the formwork and alleviate the problem that way, that's usually the most cost-effective thing to do. And we'll get into tolerances a little later today. Now, what are all the different tolerances that need to be addressed for reinforced concrete structures? The reinforcing steel fabrication and assembly. The reinforcing bars can be within plus or minus an inch or so. And the assembly itself, say of the stirrup cage, could be plus or minus a half inch, for example. Where the reinforcement is located in the structure itself, and depending on the different types of members, there's tolerances where those bars can be located. There's also deviations from the location and elevation of the structural member, say the footing, where it's located and where its elevation is with respect to where it's supposed to be. And then there's deviations from cross-sectional dimensions. So really all of these need to be looked at, maybe not in all of your typical situations, but especially in places where you anticipate any congestion to occur. But generally speaking, they all need to be satisfied and at least looked at and observed through detailing, that making sure you're not going to have any issues once you take into consideration these allowable tolerances. Okay, given that overview, some general recommendations and guidelines that hopefully you might be able to implement from the onset of a project. Like I said, I'm sure you have other things that work in certain cases as well. We're going to move on now to our different structural elements in particular. We're going to start with one-way slabs, then we're going to move on to two-way slabs, and we'll conclude today with beams. So in terms of the overall slab thickness, generally we'd like to provide a slab thickness that satisfies serviceability requirements. So as we know, ACI 318 has some equations that you can use based on the span length of how thick that slab needs to be, and then you don't have to worry about deflections. You can calculate deflections, of course, and have those short and long-term deflections less than or equal to the limiting values that are also given in ACI 318. Fire resistance requirements also need to be satisfied. Say we have a typical 2-hour fire rating. Generally speaking, that's satisfied if you provide a slab that's thick enough for serviceability. Now, the only place you might have to worry about something like this is if you had a two-way joist or a one-way joist system where that slab can be much thinner for serviceability and structural purposes than required. And if you have a higher than normal fire rating that's required, that's where you might be able to run into some issues with fire resistance. But generally speaking, if the slab is good enough for serviceability and strength, it's also good enough for fire resistance. And this last bullet point here, we're going to see this repeated many, many times today. Use the same thickness in all spans, if at all possible. You know, for architectural or other reasons, there may be a need to change the span. The thickness with respect to the span. But if there's no such need, then there's no really good reason to change that thickness. You base it on your longest span that's doing the most work and just use that every place. Now, in terms of reinforcement detailing, certainly we need to satisfy all of the ACI 318 requirements for strength and spacing. And once we choose a bar size, we'd like to use that same bar size and spacing and length wherever we can throughout the structure. Again, going back to the simplicity of it, having the same bar size at the same spacing that has the same length, this will enhance constructability many, many times over. And along with that, it's going to be so much easier to place in the field, which is really part of our constructability as well. Specifying a consistent tension lap splice length is also important. Now, you don't see this very often, but some designers like to alternate bar sizes, especially in one-way slabs, to try to reduce the amount of material. Now, that's not the best practice in the world to do for a number of reasons. You know, you have to concern yourself with a number of different bar sizes in the field. But one thing that certainly does happen is if you're using stock length of bars, and these light blue bars are smaller than these dark blue bars, what's going to happen is you're going to have issues then with respect to where the lap splices occur along the length, and they may wind up in spots that you're not permitted to have the lap splice is in. So it all goes back to stock lengths. You know, the larger bars obviously are going to have larger lap splice lengths, and that's going to be fine over the length. But when you compare those to the smaller bars, now you're talking about locations where the lap splices are going to happen where you don't where you didn't anticipate them to happen. So overall, it's not very good practice to alternate bar sizes, not only in one-way slabs and in any type of slab system, at those particular, at the same elevation. So, to save yourself a lot of grief, use the same bar size everywhere. So let's move on to two-way slabs. Two-way slabs, again, serviceability is important. Once again, ACI 318 has some empirical equations that you can use to determine what the slab thickness has to be for serviceability. What usually governs, as we well know, is two-way shear in a two-way slab system. So, we'd like to come up with some preliminary slab thickness to see if that's going to be an issue for us. And if it is an issue, generally, we like to provide these stud rails that will help us enhance the two-way shear capacity around the faces of the column. Now, in addition to that, it's more than likely we're going to have, well, more than likely, it's a given that we're going to have embedments in the slab. So it's nice to account for that as well. There's a lot of contractors, especially here in the Chicago area, will use nothing less than an 8.5-inch thick slab just for embedments. So that 8.5-inch slab for typical spans will work out well for serviceability. For the longer spans, sometimes we'll need to provide the stud rails to enhance the shear capacity. Now again, fire resistance, as I had mentioned for the one-way slab, but especially for a two-way slab, if you're going to provide an 8.5-inch thick slab or something for serviceability or strength, you're going to get more than a 2-hour fire rating out of it, no problems at all. And again, using the same thickness in all spans will enhance constructability. Now, there's a few cases that we'd like to look into that happen either earlier in the project or usually later in the project when the architect realizes, we forgot to put drip grooves in at the end of our cantilever part of the slab that's being used for the balcony. Now, hopefully that occurs before, hopefully we don't miss that in our construction when reviewing their documents, their drawings, because that could cause us issue with cover at the location of that drip groove. Now, this top detail part A shows an offset bar kind of bent up, and that's not the most, it's not probably the most best thing to do in this case. The people in the field like to use just the straight bars for a number of different reasons. So if that drip groove occurs and we have the bars that are running close to that, which will cause us some concrete cover issues, it's best to just shift those bars to either side of the drip groove, and so that they can acquire their concrete cover. I can't tell you how many times this has happened to me when practicing, that all of a sudden you look at a detail and that drip groove is there. So you scramble to get your typical detail on the drawing for that particular case. So in terms of some constructability details for two-way slabs, again, it's probably best to use the largest bar size that satisfies strength and serviceability requirements. Again, keeping in mind that we don't want to space the bars too far apart for to violate any of the crack control provisions in 318. We found that using number 4 bars at 12 inches for the top bars will help in terms of construction traffic. So as you know, there's a lot of activity going on during the construction phase, and having at least number 4 at 12, it's going to leave a good surface for the workers to walk on without displacing any of the top bars. They could easily fall off of the chairs and wind up in places that you don't want them. So having a nice stiff mat of reinforcement at the top, at least number 4 at 12, will help alleviate that particular issue. And again, using the same spacing as often as possible. So for our middle strips, there's no reason why we shouldn't be using just a minimum reinforcement at close to maximum spacing. Also, in the column strips, using the same bar size and the same spacing as often as possible. It's also important on the structural drawings to identify which layers of the reinforcing bars are to be placed in the outer and inner layers. Now, usually the reinforcing bars in the direction of the larger bending moments will be placed in the outer layers so that we get the larger effective depth to the center of those reinforcing bars. So having something in your general notes, and this is one way I've seen on some of the structural drawings. So this is a typical slab column strip detail where we have the bar cutoff points, and they have here a note that I've enhanced with a red box around it so that we can see it easily. It gives the rebar placing sequence. So in this case, all of the east-west bars on the slab at the bottom get placed first, then the north-south bottom bars, then the north-south top bars, and then the east-west top bars. You know, it's obvious until you don't do it, and then the issues come up, and especially, you know, if different bar sizes are used for top and bottom, what's the proper way to do it? Now, as we've seen more often than not, we're going to have an irregular column layout. And what we recommend to do in such situations is to use mats of reinforcement for both the top and bottom bars that are perpendicular to each other and evenly spaced. If you need any additional bars, then you could put those in at different locations where they're warranted. But having this nice grid of top and bottom bars is going to help a lot with respect to placing the bars when you have a regular column layout. Now, some people like to use a skewed bar, and they can certainly be used if so desired or warranted, but those should be placed in a separate bottom layer outside of, you know, your orthogonal top and bottom reinforcing bars that you're going to provide. So what we have here is, again, a typical layout that you may want to use in this particular case, where you have these uniformly spaced top and bottom bars. And you certainly don't have to show the bars on your construction documents. You can have a note that tells you what the bar size and spacing is in both directions. And then what I usually like to do is then provide any additional bars, including any skewed bars that are easily seen on the drawing itself. Oh, and by the way, I meant to mention this a little bit earlier, but a lot of the figures that you're going to see in the presentation today and tomorrow come from different sources, which I've referenced here at the bottom. So back in the earlier part of the 2000s, up to about 10 years ago, there were a number of articles that appeared in Concrete International that addressed exactly what we're talking about today. So you can go back, especially if you're an ACI member, you can go in and get these full articles and download those, and that gives you a lot of good information in terms of all the things we're going to cover in these two sessions here today. So you can see where this one came from, November 2012 edition of Concrete International. And as I had mentioned, on your structural drawings, it's nice to just have notes with respect to your orthogonal layout. And then if you need any additional reinforcing bars because of a change in load or span or something like those, that you can clearly identify those separately on the structural drawings. And just to give you an example of that, here's one where if you look at this particular note 1, it points out that the slab is 10 inches thick and you have number 5s at 12 on center as the bottom rebar in this mat throughout. So that's what a lot of other people like to do as well. You know, have one drawing for the bottom bars, one drawing for the top bars, and then what you see here identified are any additional bars you need within the column and middle strip. As we know, the bars that are terminated at the edge of a slab need to be developed for the full yield strength of the reinforcing bar. And generally, we will provide a hook according to what's required in ACI 318. Hopefully those hooks will fit within the slab thickness. It all depends on a number of factors, obviously how thick the slab is and how large the bar is. But in case the hooks do not fit, there's a few things you can do to try to remedy the issue. You can try a smaller diameter reinforcing bar. That'll obviously give you a smaller hook. You could use a headed bar, which, as we know, the headed development length is shorter than that of a hook bar, and it can fit with much easier within especially a relatively thin slab. Or as a very, very last resort, if nothing else works, use a 180-degree hook instead of a 90-degree hook. Now, there are some issues, as I'm sure we're all aware, with 180-degree hooks, especially at the end. You know, if you have this layer of bars in, and you can't put that hook bar in on top of the other layer, so you have to take that last bar, or more than one bar if it doesn't clear the hook, and slide that over, and then slide it back once the hook bar is in place. So it's not the most convenient thing to do, and we don't recommend using a 180-degree hook if at all possible, but sometimes you have to, and you know, this is the way you would have to do it. Basically put a note on the drawing showing where the bar needs to be initially and then where it should be after this 180-degree hook gets installed. One other thing I wanted to mention here, when we have embeds at the slab edges, this could be, say, for example, due to your facade attachments. That's another place which could cause you issues with your reinforcing bars, and you need to develop special details at those ends so that there's no interference between your hooked bars and whatever embeds you may have at that location. Now, as we know, when we have a slab column intersection, a portion of the moment at that joint gets transferred by flexure, a part gets transferred by shear. And ACI 318 requires that portion that gets transferred by flexure to be concentrated within basically 3 times the slab thickness plus the dimension of the column perpendicular to analysis. Now, that detail has to be clearly documented on the structural drawings. You have to have a special detail there for constructability, because if it's not, the bars are going to be spaced out and you may not then have the concentration of reinforcement that you need at that particular location. So I've seen this done a number of ways. I've seen it done this way, where it calls out placing half of the top reinforcement within this particular strip. The other way I've seen it done is actually having the column there and those bars actually shown on that particular detail of what the concentration has to be over there. Whichever you prefer to use is up to you, but in these cases, this is an often forgotten detail that can cause some serious consequences if it's not shown properly on the drawings. Now, beams along column lines is another place that we need to carefully look into, especially the location of the slab top reinforcing bars with respect to the reinforcement that's in the beam. As we know, the slab bars are typically placed above the top bars in the beam because of the minimum cover to the slab bars is generally smaller. So if we look at that typical detail, this is the top reinforcement that's in the slab. We're showing 0 inches here, being at the same elevation as the stirrup, so it's a fit in between where the stirrups are spaced. again, simple drawing, but you know, if the covers aren't called out and certain other things are not called out, it could cause an issue. Okay, the last segment we're going to cover today is beams, and we have quite a lot of information here to cover for beams. This is where we really get into more of the tolerances that we talked about at the onset of our session today. So let's start out again by looking at the thickness of a beam. Again, serviceability and fire come into play. And as I had mentioned before, especially for a beam, having the same depth and the width over all the spans is by far the most cost-effective and constructible thing to do. Just change the rebar as you go along the length, and that'll give you the most economical solution. For cases where you have a wide module joist system, where the joists are really not joists, they're beams because they're spaced farther apart than what ACI 318 requires a joist to be. You have beams supported by girders. If you have this particular type of floor system, and I know it's more popular in certain parts of the country than others, but if you do run across this, it's by far the most economical thing to do is to have all of the beams and all of the girders at the same soffit level. The formwork is built for these. Then the forms for the joists, as you see one here, this worker just pulled this one out. Those are at the same elevation, very easy to construct. If you can imagine the beams being deeper than the joists, all of the additional work you'd have to do with the formwork at the intersections where the joists are framing into the girders. Now let's talk about the beam width. This figure has been around forever, and it's still worth repeating because it's still very relevant in terms of what's the most economical beam width you should use in terms of overall constructability. Okay, if you look at the plan view A and that isometric right below it, that's where the formwork, and I should say the beam width is the same as the width of the column it's framing into. Has the simplest formwork. It's certainly an acceptable solution. The only issue you may come across is depending on how much longitudinal steel you have going through the beam, there could be some interference with the more interference than actually needed with the longitudinal bars and the ties in the column itself. So for that reason, the most desirable situation is to have the beam that's wider than the column. And we recommend at least 4 inches wider. By doing so, you can pass the portion of the longitudinal bars through this joint without intersecting the column core, and it gives you a little breathing room, especially if there's a lot of steel coming in from the beam. The least desirable situation, and I understand, and sometimes we certainly have to do it because of the architectural and other requirements, is having the beam narrower than the column that it's framing into. Basically because of all this additional work you have to do with the formwork. All of these special pieces have to be cut, whereas here you have the plywood that just flies by. Here you have to stop and do all of this special forming in order to get this to work. And again, there's all the bars again are going through the core of the column, so you could have some issues there. So if at all possible, providing at least a beam that's 4 inches wider than the column it's framing into will help with your overall constructability. So here's a nice example of that. Again, this is a wide module joist system. You can see the pan forms here. The rebar is all set for the girders that are going to be supporting this joist, and you can see you have a lot of breathing room here to space this relatively heavy top and bottom reinforcement that's going through the joint. Now keep in mind, ACI 318 doesn't tell you that all the bars in a particular level have to be uniformly spaced. As long as you provide the required amount of area of steel for flexure, those bars can be spaced whichever way you like, as long as it doesn't violate any of the spacing requirements, minimum and maximum, that's given in the code. So this really illustrates it here nicely, where you can see all of these bars, which are fairly heavy bars going through these. These must be some fairly long spans, 40 to 45 feet. This girder's picking up a lot of load, and by having that girder wider than the column, that really alleviates any congestion or constructability issues at this joint. Whereas if you have this relatively narrow beam going into this column, you can see all of the issues that may occur at this location. All the bars are not in here, and it looks like there's some fairly small bars that are going through the bottom, but again, in general, it's just obvious that you're looking for some congestion issues if that beam is narrower than the column. Again, sometimes we're forced to do it and we have to make the best of it, but that's when all of our other recommendations and guidelines come in terms of using the largest bar size possible to make everything fit well within that joint. Now, it warrants repeating again, using a constant beam size from span to span and varying the reinforcement as required, and use uniform width and depth, not only at a particular floor level, but throughout the building wherever possible. Having 100 different beam sizes, unless it's a very special type of structure, is not a very efficient thing to do. Selecting just a few or a handful of different beam sizes and using it as often as possible is going to help out with constructability tremendously in the project. I always like to show these two tables because they're very useful. Once we've determined the area of steel that we need in the beam and how many square inches of steel that we need, the code requires a certain minimum and maximum spacing. Minimum spacing so that we can fit the concrete in between the bars, and a maximum spacing for crack control. So for minimum spacing, if you take those requirements that are given in ACI 318, you can come up with a table like this that tells us what's the maximum number of reinforcing bars that are permitted in a single layer. Now, this particular table is based on the overall bar diameter that I showed you a number of slides back, that includes the deformation on the bar. It includes a clear cover to the stirrups of 1.5 inches, a nominal maximum aggregate size of 3/4 inch, and it assumes number 3 stirrups are used for 4, 5, and 6 longitudinal bars, and number 4 stirrups are used for number 7 and larger bars. So if you take the requirements that are in 318 for minimum spacing, and given all of these assumptions, you can come up with this table so that if I want to use a number 9 bar in my 24-inch wide beam, then I know the maximum number of bars I'm permitted to use is 8. So I don't have to go through all those calculations all the time to determine what that is. It's a very handy table to have when you're sizing the reinforcement and selecting, I should say, a reinforcing bar based on the area of steel that you need. This will solve all of your constructability issues for maximum number. And we can do the same thing for the minimum number of bars. It does depend on the diameter of the bar, but you'll see that if you go through the calculations for a particular bar size, it works out to be just about the same number of bars as well. So this is for the minimum number of reinforcing bars that you need in a particular layer, single layer. And this is, again, grade 60 reinforcement. We use the overall bar diameter, and we use a distance from the surface of the flexural reinforcement to the tension face of 2 inches. So again, you can go through the calculations and it will give you the numbers that are shown here. So if I go back to that number 9 bar again, I really don't need to have that particular bar size, but for the 24-inch wide beam, it means I need 3 of those number 9 bars. So if I'm anywhere between 8 and 3 bars, then I know I've automatically satisfied all of the spacing requirements for a 24-inch wide beam from ACI 318 without having to do any calculations if the assumptions that we've made here are the assumptions for your particular case as well. And you can easily come up with similar tables for other types of material properties. So very, very handy tables to have. This will automatically satisfy any constructability issues that you'll have as well. Now, for the case of a beam that has multiple layers, parallel layers of bars, and we provide hooks at those ends, there can be cases where, because you can't, these are parallel, they can't be in the same, they can't be at the same location, the end of the hook. It's possible that these bars that are on the inside here may not be able to be developed properly. So that occurs when you have these larger bars, number 8s and 9s, and trying to hook those big bars and maintaining your development length may not be possible, especially based on the size of the column that these are being embedded into. So one possible solution for this is to use a headed anchor. We call them headed bars now. This article's from 2011. So headed bar will help alleviate that. And these bars mitigate congestion, not only in beams, but columns, other elements as well in your mat foundation that's supporting a big shear wall. These will help because those are, especially when you're using very large bars where the hooks are relatively large. The coordination between the fabricator, the contractor, and the placer is very simple, especially if you use the same bar sizes. You just come out, place the bars in the field, and you're done. There's really no issue about any insufficient development lengths in these cases. Very easy to place, and overall efficiency at the job site is improved tremendously. Just something to keep in mind if you run into congestion issues with your reinforcing bars. Now, the next few slides, we're going to go over lap splices and beams, in particular, the bottom reinforcing bars, because this is usually where we can run into some issues. Now, I would imagine that the typical detail that's shown here, which is labeled number 1, is on most of our structural drawings, where the bottom bars are lapped directly over the column. Now, that's by far the simplest to detail. That's where they should be, away from the maximum positive location, positive moment location. So very simple to detail. They're very easy to use when the beams are wider than the columns, and you don't need any additional reinforcing steel, which you'll see in our next sets of details you may need in those particular cases. Some of the disadvantages of this typical detail is you can have a lot of congestion at the intersection between the beam and the column where these lap splices are occurring. So, this is nice and simple here. Everything looks good, but let's keep in mind that we've got a lot of other bars coming in here from the longitudinal bars in the column. And so when you have all these additional lap splices here, the steel, that could certainly cause some congestion. That's one disadvantage. The other disadvantage is that if your beam cages are prefabricated and these are dropped in, sometimes they're dropped in one span, sometimes they're dropped in 2 spans, depending on the geometry. If you can imagine these two pre-assembled cages trying to come together and lap splicing the bottom bars like that, that could be some issues there with the installation. So There's certainly some advantages, there's some disadvantages. So it's not only in this case, but the other cases I'm going to show you here, it's a lot to do with what you have in your actual project, what might be the most suitable solution to use. So another possible solution is to take half of the bars, bottom bars, and lap splice them on either side of the column. Okay, now that certainly eliminates that congestion that we were talking about before within the joint. And once again, there's no additional steel that you're providing here, so no additional cost for any additional bars. The only issue, again, comes from pre-assembled cages. If the cages are pre-assembled, having this type of connection to make is really much worse than having the connection we were talking about in the first situation. So knowing that, again, knowing that at the onset, you probably aren't going to know that until you get the placing drawings back. But just again, thinking about span lengths and seeing what might be the most beneficial solution is something to think about at the onset. Now here's another possible solution where you take the all of the bars and lap splice them just outside the column core, okay, on either side of the column. So instead of taking 50% on one side, 50% on the other, you take 100% on one side of the joint. Now, this is, if you're going to have pre-assembled cages, this is by far the simplest to use. And again, no additional steel is required. The only disadvantage you have here is you have to ensure that the cages are oriented correctly if the installation begins at the center. Otherwise, you're not going to have the right type of connection, and it's going to be all messed up. But it's a very useful type of lap splice location, especially if you had a lot of large bars going into a relatively small joint. The final detail we'll look at now is where you have all straight bars and the main reinforcing bars from your beam do not pass through the joint at all. What we have then is additional reinforcement that gets lap spliced to those bars. So that takes care of any congestion issues that you have. If you have pre-assembled cages, this is by far the easiest to use. So you drop the cages in, then you install these additional bars and tie them down, and you're all done. The only disadvantage is you have this additional reinforcing steel. Now they're showing it here kind of kinked, kind of bent, but you're going to use a straight bar here and lap splice it so it gets your full development length. So number of different options for different cases, just something to think about other than that first option, which I'm sure is on a lot of our structural drawings, where could cause you some congestion at that joint. Now, when we talk about stirrups, if the cage is not pre-assembled, we want to try to avoid one-piece stirrups, because trying to place, especially the top bars, trying to thread them through is not the easiest thing in the world to do. It's by far easier to have a stirrup that consists of two parts, your outer stirrup with 135-degree hooks that are connected to the two end bars, and then a cap with a 135 and a 90 at the end. If it's pre-assembled, it doesn't matter. But if these are being built in the field, then having this arrangement, this two-piece stirrup arrangement, is much easier for overall constructability and placing in the field. One thing I used to find on the when I was doing the peer reviews is you would have a note that points to the stirrup saying 8 at 12. So is that 8 the number of stirrups or the number of spaces? So I'm sure, in our drawings we identify those correctly, but sometimes, things get lost in translation and you can come up with a generic note that could be confusing to the detailer. When you have relatively wide beams, and if you're not aware, for the first time, ACI 318 addresses what the maximum spacing is between what the different legs in a wide beam. If you have this wide beam stirrup configuration, what you see in this particular section of the wide beam is a set of 3 different closed stirrup configuration. Now, this is not very advantageous for a number of reasons. One, when these are placed in the field, if you had a stirrup that goes the entire width of the beam, it's a lot easier to place because now you don't have to worry about the cover. Well, in essence, you have to worry about it, but if it comes out with one piece, then you can evenly space it from the side of the formwork and you're done. When you have all of these different pieces, then somebody has to start measuring of what's the correct cover that needs to be provided in those cases. So that's one disadvantage. The other disadvantage is having these closed one-piece stirrups once again. If everything's being built in the field, trying to thread the bars, especially through these wider beams, is going to be a very difficult undertaking. So for those 2 reasons, it's best not to provide stirrup configuration for a wide beam as shown here. What's better to do is to have this one blue outside stirrup that traverses the entire width of the beam, 135-degree hooks around the 2 end bars. And then I'm going to show you 2 different options. One where you have these interior 135-degree stirrups around the other ones, and then a stirrup cap that traverses the entire width. That's a very viable solution. Or another viable solution is where you have the full stirrup traversing the entire width and your cap, and then instead of having 2 separate ones, you have kind of this nested type of configuration. Either one is fine. It eliminates a lot of the issues that could happen in the field. Okay, drip grooves with beams. Again, hopefully this information is provided prior to construction. Otherwise, you're going to have a cover issue. So our best bet is if we know we have a drip groove, just size the beam and reinforcement and such, considering the additional cover that's needed because of that drip groove. Beam intersections can cause a lot of headaches, especially when the beams are the same depth. If you have a typical detail and it shows what the cover is to the longitudinal reinforcement in the beams, that's not going to be enough, because if we have these beams that are framing into this other beam, you can see if the cover to this beam is 2 inches, and if we don't have any additional information, these bars are also going to be at least initially detailed, assuming it was 2 inches, knowing then that you're going to have an issue here with the bars coming in at the same elevation. So it's nice when we have an intersecting beam situation to specify what the cover needs to be for the reinforcement in that particular beam that's framing into another beam. Now, when the beams are different depths, it's not such an issue. Okay, you can have the same cover and things will work out fine. Now, this next 2 slides, it shows, this is from one of these Concrete International articles. It shows what you can do by having offset bars and what the procedure is. So I'll let you read through those. I'm not such a fan of this particular one, especially because of the offset bars and the placing difficulties. I would rather use, a larger cover, if at all possible, for these bottom bars that are the same depth for both beams. And again, no matter what your situation is, it's important to have the layering sequence on your structural drawing so a contractor is aware of how this needs to be built. We'll take a look at steps in beams. Now, if you have a step, that may be because you're going to have a raised floor for some reason, or there's no way other than to bypass some HVAC equipment. If you have a step, and of course this is not always possible, the best place is at a column line or where there's another support by a beam. That would be a natural location for it to occur. More often than not, it's not going to occur there. So what do? If that top step is less than or equal to 3 inches, generally what you could do is to take the beam that has the smaller depth, D1 in this case, and design it for that depth. So the flexural reinforcement for that beam will satisfy the strength requirements for this depth, considering the extra concrete is dead load, but then making sure we provide some additional bars for crack control in that portion so we don't have any issues with the concrete there. So that's one thing you can do. Now, if the step is introduced late during the construction, during the design stage or early in construction, there's a couple things you could do. You could either bend the top bars, which I'm not a big fan of, again, having any type of bars that are not straight. One other thing you can do is to take the top bars that are in the beam here, design it again for this situation, and then splice those bars, lap splice them with the bars that are already in the top, which would be straight in this depth here. You may need to provide some additional stirrups at this location. Now, this lap splice would be a non-contact lap splice. So ACI 318 has requirements on what's the maximum spacing between the center of the bars to make it a non-contact lap splice. In some cases, you know, especially if there's any type of issues, constructability issues, having this non-contact lap splice can be very useful. Now, if the top steps are greater than 3 inches, then what we have is a situation of where that actually occurs. Sorry for that noise, folks. I'm not sure if you're going to hear it or not, but sorry for that. As we were saying here, if the top step is greater than 3 inches, the detail depends on where the step occurs. If the step occurs when the top steel is not in tension, then you can provide just a typical lap splice with the bars. However, if that top steel is near the support, then you're going to have to provide something more than just a typical development length. It has to be a Class B lap splice. Top steps that occur at columns or beams, those are the most economical place to have them. We can provide hooks, or we can just carry the reinforcement out into the other slab, into the other beam. If the bottom step occurs near a column or a beam, hopefully we had the opportunity to carry it all the way to the column. Sometimes we cannot. Then what we have to do is start splicing all the bars and putting additional reinforcement there for stirrups. When the step is greater than the depth of the beam, you can have a couple different situations here. That particular step can act as a hanger or as a support. So if you can imagine this beam at the bottom being a cantilever beam and this beam at top being supported on one end, and then by this one here, you would detail everything properly in that sense. Or if this were the cantilevering out and this was your support, it could hang from that beam, depending on the situation. Finally, we're going to look at a couple of tolerance issues that you come across very often with beams. The first one we're going to look at is cover to the transverse reinforcement. If you don't have a copy of ACI 117, you need to get one because this is crucial in a lot of cases for the overall constructability of a particular beam element. So this is the beam we have, 24 inches deep, 28 inches wide, and we're going to look at an issue that you might have with the cover to the transverse reinforcement, considering the tolerances that could occur as specified in ACI 117. First, we look at the cover to the transverse reinforcement. In the 117 document, the beam thickness can be a ½ inch greater than specified or 3/8 of an inch less, okay? The overall height and width of the rebar cage has a tolerance of plus or minus a ½ inch. The top cover then, considering the worst case scenario, and by the way, what I'm going to show you here is, the perfect storm of all the tolerance things happening at the same time. Doesn't happen very often, but it can. And these are like the worst case scenarios. So you may not ever see this, but in case it does happen, we wanted to suggest a few things that you might want to look into. So if you consider that the beam thickness is a ½ inch larger than specified, and is the overall height of the cage is a ½ inch greater, and the beam thickness is 3/8 inch less, you can have a top cover that's reduced by as much as 7/8 of an inch. Now, ACI 117 gives some tolerance requirements, what's acceptable for the cover. So the resulting cover from that 7/8 inch is you've specified an 1.5 inches, take 7/8 off, you're left with 5/8 of an inch left with respect to the cover to those number 3 stirrups. The concrete cover tolerance in ACI 117 is minus a ½ inch. So the acceptable cover is 1 inch. That's greater than our provided cover of 5/8 of an inch. So even though everything may have, you're looked at properly with strength and everything and cover, you could still run across a situation where the provided cover is less than the acceptable cover. And here would be a great place, we'll look back at here, if at all possible, to adjust the formwork in the field if this is found. If this is a pre-assembled cage, it's going to be very difficult to try to make the reinforcement move up to get that additional cover. Okay, and this section just shows you all in a pictorial form all of the things we were talking about. So the stirrups being up higher than usual, the beam being less than usual, and that's where that 5/8 inch cover comes in. This is the case we talked about before with intersecting beams. If we don't have a special detail or a special cover for this cover A and this cover B, and we have it just at a 1.5 inches, we're probably going to get some type of an RFI from the detailer, or the detailer sometimes takes it into their own hands and provides larger cover for those bars. I think it's best that as a licensed design professional, we provide that cover. Now, we don't want, again, the dreaded double hooked bar. So what we'll do sometimes is put in straight bars and then have this hook bar come in that's lap spliced to the green bar. Tolerances are also very important when we talk about measuring the thickness of a beam. So here we have a 30-inch deep beam, 24 inches wide. Where should we specify the thickness on our drawings if we have a slab that is not perpendicular, that's sloping with respect to the beam? Well, if the beam thickness is measured on the downhill side, on this side here, the stirrup depth is going to be the whole depth minus the 1.5 inch and 1.5 inch cover, which is 27 inches. However, if the beam thickness is measured at the beam center line, when you take all the geometry into consideration, the stirrup depth is only going to be 26.25 inches. So that's why it's important on the drawings when you have these slope slabs to specify where the depth of the beam is being measured from, because you can see there's quite a difference between the, well, not a huge difference, but when it comes to trying to fit things in the field, it could be a big difference. Finally, again, beam elevations, when you look at deviations of tolerance, this could be like in a parking structure with a ramp. Again, depending on where you're measuring things from and taking into consideration the 3/4 inch deviation from elevation tolerance, you can wind up with something less than the specified 7-foot clearance. Could go down to, in this case, when you look at the geometry, 6 foot 9.5 inches. So that certainly would not be acceptable. And there's, again, certain things you need to work out in those particular cases. So what we covered today was basically a general definition of what constructability and specifically what it means for steel reinforced concrete members. We went over some general recommendations and guidelines that can be utilized to hopefully enhance constructability, which comes hand in hand with savings in time and cost. And finally, we looked at some typical tolerance compatibilities that we come across when we have especially beam structures. So hopefully you found some of this information useful. Robert, I am going to turn it back over to you.
All right, thanks, Dave, for that informative webinar. Audience, please use the question box in the control panel to ask a question for our presenter. We will try to address as many questions as we can. And Dave, early on, someone came in with a question about headed bars. He
Yes.
said, are headed bars more expensive than hooked bars?
Well, I would hope I could answer that for you, but coming from a trade association as such, I'm not permitted to talk about any costs. So you'll forgive me for not being able to answer that question for you. I would certainly contact your local supplier, local contractor. They'll give you a much better idea of what the relative costs are between the two.
Okay, fair enough. Another question. In designing an exterior beam supporting a concrete one-way slab, for instance, do you recommend using the same width and depth for exterior and interior beams, even though those exterior beams support much less load?
Again, it depends, Robert, on the situation, but it would be great to do so because of the formwork. You know, repeating the formwork means repeating, that has that ripple effect as I was talking about before. I would certainly recommend it, even though it has less load. Sometimes those edge beams will be subjected to significant torsional load, so you may want to have that depth there for structural purposes as well.
Okay, another question. Drop panels or column capitals are sometimes used in flat slab floor designs to reduce the thicknesses of the flat slab. Can you discuss advantages and disadvantages designing these drop panel connections at columns? Should we avoid drop panels at slab column connections?
Well, it depends on who you talk to. Mostly the contractors don't like to do them because it's extra time for the form work, and it's not as fast as just putting up one sheet of plywood, putting the rebar in, and then dumping the concrete in. So there's a little extra time and money that goes into these drop panels. Now, there's cases where you may not have any other choice for whatever reason. Certainly, now a drop panel will allow you to decrease the thickness, but a shear cap will not. So if you're having shear issues and for some reason the headed studs are not a solution, then I would recommend using a shear cap. A drop panel will permit you to decrease the slab thickness. It will also give you a larger effective depth for the reinforcing steel going for your negative bars. So that may be able to decrease the amount of flexural reinforcement you need at those support locations. So again, this is a topic that should be addressed early on in the project, and especially with the contractor. Are they available to get the headed studs? Then by all means use them. If not, then maybe just a shear cap may be available or applicable. So again, project dependent, and that's about all I can recommend in this particular case.
All right. You talked about hooked bars, and this person asked the question: can the hook be rotated away from the vertical plane to fit into the slab?
I've seen that done. You just have to, you have to make sure, especially if it's a thin slab, you want to make sure that there's enough concrete, surrounding that hook. And, it depends on a number of factors, but in general, I would say yes, it's certainly permitted to do.
Okay, that's fine. I have a person that's got a specific question, and it may allude to tomorrow's talk about columns and footings and studs, but I guess we have a little time. We might as well offer it to you. Following
Sure.
question may not directly relate to this topic, but nevertheless, your comments will be appreciated. Concrete columns designed for a fairly large exolo, 500 kips, and seismic, had all dowels from the foundation misaligned to overcome a construction default. The contractor ended up bending the rebars, I don't know, number 8s or something, 90 degrees horizontal, and then bent again to vertical to bring the bars into the actual location. Do you have any comments on that procedure?
Oh, goodness. Yeah. If if this were not, let's say if this were a high seismic zone where, seismic design category D or above, I certainly would not recommend it to be done because of the, just putting the bars through the extra stress like that. We do have a tech note here that says in non-seismic applications that you can bend a rebar once and it should maintain the properties that you would expect from that bar. The only thing I'd worry about, because it's high seismic, of bending the bars again like that, there's nothing out in the literature that says you can't do it. I would just be very wary of it because of the extra bending that you're putting those bars through.
Yeah, that's a unique situation.
It certainly is, yeah.
Yeah, all right, we have got time for this last question. Should the top and bottom bars for supported sides be equally spaced? Can you place like the top bar and the bottom bar at different spacing?
Oh, certainly. Yeah, those could be at different spacings. Again, depending on the situation, it's nice to space the bars out at a reasonable distance, like 12 inches on center, especially the top bars, as we were talking before. It gives a nice working platform for the people that are placing the bars and all the other traffic that occurs. Once you specify a certain spacing, it doesn't necessarily have to be the same for the top bars. It would be nice if it were, but it doesn't necessarily have to be, as long as it's consistent. Having the same spacing in the column strips everywhere, if possible. Same thing in the middle strips, top and bottom. That, top and bottom doesn't matter too much, but having them the same within those different widths would certainly enhance constructability.
All right, thanks, Dave, for answering those questions. Audience, please remember to fill out our brief feedback survey that you will see as we exit the webinar. If you're looking for continuing education credit for this webinar and were unable to join us for the duration of the live webinar, be sure to complete the online quiz at aciuniversity.com. Go ahead and move the slide, Dave. The following are upcoming webinars that include Constructability, our other Constructability series, which also includes tomorrow's presentation by our same speaker, David Finella, on design and detailing of columns, walls, and foundations, and others. So thank you for joining us. We hope you will join us for future learning opportunities. Have a good day. Thanks.
Thank you.